Hi everyone, I'm going to record a lecture 14 part 1. I don't know how far we're going to get into how many different parts of lecture 14 I'm going to do. I'm going to at least do 50 minutes, so set timer for 50 minutes. Okay, I say 50 and it always does 15, and so bear with me for a second. Set timer for 51 minutes. All right, you're going to get 51 minutes. That's good. So our circuit, okay, all right. What have we been talking about lately? We've been talking about inductors, right? So before we start talking about our circuit, let's rehash our inductor situation. We've been doing inductors that are this symbol, so I didn't draw a very good one over in my circuit, but that's our inductor. I labeled it with L just so you could tell that it's an inductor. And we're going to basically do what we did with RC circuits, but this time we're going to do RL circuits, okay? And eventually we'll do RCL. So let's check it out. So first of all, we've got our EMF. It's running through from positive to negative, so that means our current is going to go around the loop in a clockwise fashion, and it's going to run through our inductor. So it runs through our resistor first, runs through our inductor, and then goes to the other end of the EMF. Okay, so we're going to apply Kirchhoff's rules to this, and I'm going to do a loop, my loop number 1, like that, because I only really need one loop. And so we're going to do loop number 1. We have no splits. There's no split happening, so the junction rule, let's do the junction rule, doesn't apply. Okay, so what is it based on? Conservation of charge. Okay, but doesn't apply, right? It's clear. I hope it's clear to everyone why the junction rule does not apply, right? We don't have a junction and a split in the current, okay, going off somewhere else. So we don't have to think about that. 2, we've got the loop rule. Well, I just showed you what loop I'm going to do. So I assume you guys get that we're going to do the loop rule. All right, so here's the loop rule. We're going to do our loop. We're going to go from negative to positive across the EMF, so that's going to be a positive EMF. Our current is dry. It's going to do a downfall across the resistor, so our current times the resistance is going to go down. And then we have something, okay? And are we going to add? Are we going to subtract? Nobody knows. And to this day, nobody has ever figured this out. I'm just kidding. We know. So we're going to do our loop rule and see if we can figure out what happens here with the induction. Okay, our inductance is going to come into play, but what is it that's going to actually come into play here? Are we gaining? Are we losing across the inductor? Okay, so huge question. So we're going to figure that out, and it looks like Leope rule, and I don't want Leope, I want loop. There. Okay. The loop rule is based on conservation of energy. Okay, so let's see if we can figure out based on a use of conservation of energy, let's see if we can figure out what we're gonna deal with here. So we showed that our total energy stored in the inductor is 1/2 Li squared. All right, so we've got our current flowing through this thing, and it is definitely storing energy, and it's 1/2 Li squared. All right, so our potential, our power lost, we also looked at the power lost. And we're going to say that our power lost is equal to our EMF I've got EMF L, and I think what that means is I think I'm dealing with the potential drop across L. Okay, so there's a point, we're going to call it the point here. Let me draw our L. There's a point here, and our EMF L is this. Okay, it's just the drop from A to B, okay, across that point. Let's get rid of those guys, and we'll do B. Okay, so from A to B, that's our EL. Okay, so that's our potential drop across, and we're going to multiply that by our current, because P equals IV or VI, however you want to talk about it. And of course, we know that that's du dt. Okay, so good. Now let's do du dt. Of course, our current is I of t. So when we do this, these things are constants, and we're really going to end up taking the derivative of I of t. Okay, so we're dealing with that. Shall we move up a little bit, give ourselves some room? So what is du dt? So that equals I. So du of t dt. Well, let's figure that out. We're going to put a 2 out front. We're going to divide by 2. We still have the L, and we've got di of t dt times our I of t. Hope everyone sees that. I don't, should we go through and talk about why that's true? Am I doing... I think, you know what? I'm gonna do it. I'm gonna do the integral or the derivative with you guys. Let's do the derivative together. That way you can, I don't know. I'm just gonna do it. So let's start from the beginning. All the constants, everything, the derivative slides through, right? It's going to slide through all of our constants, and it's going to leave us with this. Okay? And so that is going to equal our 1/2 L. And then we're going to multiply that. So we're going to do the derivative of the first I of t. Okay, we're doing the derivative of the first one, and we're multiplying by the second. And then we're going to let the first one slide by and do the derivative of the second one. Okay, because it's I squared, right? So we've got one, and then we've got the other. Okay, so good. So what do we have? We've got two of the same thing, right? Two of the same thing. So our du of t dt is equal to 2 over 2 times L, and then I'm going to write basically the same thing that I wrote before, but I don't know. Let's put the I of t first and then d I of t dt. How about that? Is that a better way to do it? Okay. So that solves our problem. All right. And if that's equal to P, which is equal to our EL times I, and we can put I of t because it doesn't really matter, then that means this is our I of t, and the rest of it is our EL. Okay, so of course that goes to 1, and we're left with EL, our potential drop across there, which is basically what we're doing when we do our Kirchhoff rule. We're just adding and subtracting potentials. Is L d I of t dt. Okay, so good. We have found it. We have found our way. And solving all of this, let's go back to our Kirchhoff equation. So we've got the E for the battery. We've got our minus our I of t times R. And we're going to lose a power drop across this thing. Okay, so it's going to be negative, and this is the power drop. Okay, voltage drop. I'm sorry, not power drop, it's voltage drop, and we're going to lose this. And that equals 0. So we have filled in the blank, and for our loop, that's what we've got. So what is this equation? What is this equation? I don't know if you guys have had differential equations yet or not, but this is a first order differential equation. Differential, that's this. We're doing a differential, we're doing a derivative. Okay, and it's a first order differential equation with respect to, or they say in I of t. Okay, so if I of t was an x, then it would be a first differential equation in x. Or if it was a y, it would be in y. Or if it was some other thing, it would be in that. But it's not. It's an I of t, so it's a first order differential equation in I of t. So when we did this for RC circuits, what did we find? I'm going to write down, let's put a number 1 next to this. All right. So let's switch out the inductor for a capacitor. Do you need me to draw that? So we've got our this, but now we're putting the capacitor back in, and we're going to get the same type of an equation. We're going to do our loop, right? There's our loop 1. And what did we get when we did that? We got our EMF minus our R times dq of t dt, because that's I, right? Minus q over c equals to 0. Again, a first order differential equation. However, this one is in Q. Okay? First order diff EQ in terms of Q, of T. So when we solved that, our solution was Q of T is equal to this big Q times 1 minus e to the minus t over tau, right? And our tau, of course, was equal to our RC. And so this time we're going to get a similar solution, all right? We're going to end up with a similar solution for equation 1. So what do we get? So let's deal with equation 1. And what is that going to do for us? Let's just solve it for L d dt of I of t. We're going to solve it for that, and that is equal to our EMF minus R. I'm going to put the R first and then the I of t. Okay. Now, we're going to split this thing up into a left-hand side, and right-hand side. Okay? And we're going to come to some conclusions about the left-hand side and the right-hand side, and do things that way. However, I don't want to split it up into left-hand side or right-hand side yet. Why? I'll tell you in a second. You're gonna see the magic. In fact, I wrote I should have been writing it that way up above, but writing it this way down here. So di of t dt. Should have been doing it whatever. Let's just stick with what we got. That's fine. Everything's good. All right. So here's the thing. On one side, I want my di of t. Okay? And anything that happens to go along with it in the I of t realm. Okay? On the other side, I'm going to put my dt and my L. So this is the same equation, just solved a little bit differently, so that on one side I have di of t, and on the other side I've got dt. And everything that's just a constant I threw down here with this, and then all the stuff that is part of anything that has to do with I of t, went on this side. So this makes our left-hand side, right-hand side work, and it should be a little bit more understandable this way. Why? Because we're going to integrate, right? And we're going to integrate on one side, we're going to go from 0 to t. This is on the right-hand side. And then on the left-hand side, we're going to go from 0 to I of t. And then I'm going to do one side and then the other side, okay? So let's do it. Before we do, I suppose I'll integrate. So here I'm going to integrate from 0 to I of t. And we're going to do di of t and e minus r I of t. And that equals our other side. We're going to integrate 0 to t dt over L. Good. So again, left-hand side, right-hand side. So let's do the easy one. And you're all like, the easy one? Well, that, I guess, would be the right-hand side. And I agree with you. So the right-hand side, 0 to t dt over L. And that equals 1 over L, because that's a constant. We're going to put that out front. And we're going to t minus 0. So we end up with t over L for the right-hand side. Cool? And that's so easy. You guys like falling off a log. Let's do the left-hand side. The left-hand side, 0 to I of t. And di of t over our EMF minus r times our I of t. We got to do a little substitution, okay? So what do you do? Do you guys use u and v anymore for substituting? Whatever you want, substitute it however you want, whatever variable you want to do. We're going to get back to the stuff that we're calling it anyway. So u equals this. So what is du equal to? Du is equal to minus r di of t. So that means if we solve for di of t, because that's what we really want, right? We want this di of t in the numerator. We want this bit right there. So we're going to solve it for that. Our di of t is equal to minus du over r. So we've got a little bit done. What's the other thing? What's the other thing? What is I of t in our situation? It is, we've said we really want to now go from, we're doing du, but instead of du, we're going, in du, we're going from 0 to u, okay? But u is equal to, so we're going from here to u, but u equals e to the r I of t. So now our left-hand side has an integral. We're doing we're going to go all the way up to here now from 0, and let's put in our stuff. So we've got du. Don't forget our minus sign. Let's put our minus sign in there. And we've got r u. The r can pop out, right? We can pop that r right on out of there. And we're left with the natural log of u, right? We're going to evaluate from 0 to up here. Cake and pie, baby, cake and pie. So the should I do it right here? Okay, so I've got minus 1 over r, natural log, and then we're just going to substitute in our stuff. I'm going to substitute in, you know what, I did it wrong. This is not 0. That is not. And it's obvious that it's not 0. When I of t equals 0, this bit equals 0, and we're left with epsilon. So, sorry everyone, I messed up our limits. So we got to go from here to there. Yeah, better. Okay, sorry about that. So let's do our I of t over our e. And we're doing the natural log of those things. Fine. Keep the negative sign. All right? Don't flip the natural log over to get rid of the negative sign. We want to keep the negative sign. Okay? So now we can put the right-hand side equal to the left-hand side. And so on this side, we've got our natural log over this. On the right-hand side, we've got our, where did I put it? That's our right-hand side. So I'm going to put my t over L. And now I'm going to just do all the constants on one side and the natural log on the other, because what are we going to do? We're going to take it to exponent, right? We're going to do the opposite of the natural log, which is the exponential e. So I'm going to flip everything. I'm going to get rid of this and put it over here with this guy. So this is negative, and the r is now in the numerator. And great. And now we can do our exponential thing. So let's do that. So now we have okay, now we've talked about this before, I'm going to do it again. Inside any argument, this is our argument for the exponential function. It's got to be unitless, okay? So that has to be unitless. So let's just look at minus t times r over L. So this whole thing is unitless. If it's unitless, I can now do another thing where I say it's minus t over tau. Both are in seconds, okay? And what does that mean for our tau? That means that tau is equal to L over R. All right? So we can then rewrite the whole thing with our, I'm going to just rewrite the whole equation because I'm not lazy. I want you guys to see the whole thing, okay? Good. So that's what we get. Now we really, really want I of t. Okay, so what is I of t? I of t, if you solve that whole equation, you're going to get, I'm not going to do it. You can go through, do the algebra, and solve for I of t. It'll be simple. You're going to get a nice form of this. Okay? Should be straightforward. This is our I of t stemming from our work with the left-hand side, right-hand side deal, and we integrated and all that stuff. And we ended up with this. And what do you think tau is? Tau. And I'm going to put tau L here. So tau L is L over R. It is our inductive time constant. And I don't want to say equals. I want to just write is the inductive time constant. Okay, and it's equal to L over R. All right, it's equal to that. Boom, boom, boom. L over R. Our inductive time constant. So, the next thing, of course, just like we did with capacitors, we're going to graph it. But it's kind of simple. And I hope that it seems clear that there's a maximum, right? What is our maximum? Well, that's our total voltage divided by R. So should we redraw our circuit? Here's our EMF. This is just to remind ourselves what is happening in our circuit. We're going to come down. We're going to do some loop-a-de-loops. And then we're going to come back over. We've got our plus side. We've got our minus side. Here's our L. Here's our R. Fine. So initially, our current obviously is going to be a maximum because our I max is this E over R, right? That's our I max. Everything else is going to subtract from that. It's going to go nothing but down from there. why is that graph at t equals 0, that's 0, we're at I max. When t starts to grow, we're going to drop down from I max till eventually t gets all the way to infinity. And we're at minus infinity. That means we're at 0, and it's 1 minus 0. Oh, that's why. Okay, so I'm wrong. Yet again, in my brain, I was thinking we started out at I max, but we don't. We start out at 0, okay? So at the very beginning, when this is 0, we've got 1 minus 1, which is going to give us 0, okay, at t equals 0. So our current at t equals 0 is 0. So we've got this inductor basically absorbing all the current that goes through this system. Okay, so the inductor absorbs all the current going in. Gradually, we're going to go to, we're going to say here's t, here's I max, and this is our I of t. And I just showed you that we're going to start out at 0, at t equals 0, and we're over an infinite amount of time, but it actually doesn't take that long. We're going to end up at this max, okay? So we can come over here and we can say, oh, well, it's the exact same thing that we did before, so we can come over here and do 0.63 of I max. At 0.63 of I max, we'll be at this point here. This is our tau. That's our time constant tau. And then we wait and do another tau here, and we'll have doubled our graph. Not, you know what I mean. It's exponential growth, so to a point. So this is tau L 2 tau L. Okay. Do I want to talk? I think you guys get it, right? Eventually, we're going to have current where the inductor doesn't slow the current down at all, okay? And our current at t equals, I don't know, around 6 or 7 t, it all depends on how close you want to get to I max, but eventually I t equals, I don't know, some people would say 5 tau L. So at that point, we're roughly I max. Okay. Let's do an example. I think an example is in order. Should I keep? I'm going to rewrite it. I'll rewrite it. So let's do an example. Let's do, we're going to look at t equals 60 seconds. And we're going to say that our EMF is equal to 12 volts. our resistance is equal to 5 ohms. And our inductor is equal to 3.5 henries. Fine. So there's a couple of ways you can do this, but we want I of t. Okay? So I of t at this situation. So we're going to put our E here, our R there. We've got our 1 minus E to the minus T times R over L. Okay, we can stick all those things in there, and that's going to give us before I do, you want to figure out what E to the minus T R over L is. So what is that? That is 5.95 times 10 to the minus 38. Okay, so when you do that, if you don't come away with 0, like 10 to the minus 38 is as close to 0 as just about anybody could get. Well, you can get a little closer, I guess. You could be 6 times 10 to the minus 38. But it's pretty close. So I don't even think your calculator would, I don't know, maybe your calculator does it. But if you were to do 1 minus that, you essentially get 1 minus 0 is 1, all right, if you were to do that in your calculator. So our I of t is equal to I max, and our I max happens to be our EMF over R, and that is 2.4 amps. So it didn't take much. It didn't take much time, and 60 seconds, and for sure, 60 seconds, and we were there for sure. I'd just like to know what is our tau of L for this situation. Just curious. So what is it? It's L over R, and so that's 3.5, and we're going to divide by 5 ohms, and of course that's in seconds. So henries divided by ohms gives you a second, if that tells you anything, and that ends up being 0.7 seconds for tau L. Not cal L, tau L. Not Superman's dad. Or is that Superman? Superman's dad. I don't know. Okay, so it doesn't take long. 0.7, 60 seconds. How many taus did we see? So we can take 60 and divide it by our 0.7, and that'll tell us the number of taus. And how many taus did we see? That's a good question. I didn't do this earlier, so 60, enter 0.7, divide, 85 taus. In fact, it's almost 86. So 60 seconds is way too long to wait. I should probably change it in my notes. We should probably change it to 10 seconds. What happens at 10 seconds? So e to the minus 10 times 2.5 divided by 3.5. What is that? So 50 divided by 3.5 and divide, and that's 100. What? That's not right. Enter. 3.5 divide. That's better. Okay, so, and I need to make that negative 14.2857 whatever. I need to make that negative, and then we're going to do e to that, and we end up with 6.25 times 10 to the minus 7. Still very small and close to so after just 10 seconds we basically are sitting at Imax, right? Your computer or your calculator might give you, let's see, if I make that negative and add 1 to it, yeah, I mean that's 0.99999375. That's basically 1. So 10 seconds is all we need for this 10 seconds is all we really need, and we're still going to end up with 2.4 amps. Okay, so even after 10 seconds, we've got 2.4 amps. So yeah, I'm going to go through here and do t equals 10 seconds. Just make a little note. That gives us e to the minus tau, t over tau is equal to 6.25 times 10 to the minus 7. That's pretty freaking small, and then we'll still end up with that. And we know that. Okay, so good. Let's move on. This is what I do. You ask questions. This is how you should best go through, and you just ask questions. What if this? What if that? What does this mean? What does that mean? So I wanted to know. I wanted to know more about this situation. So 10 seconds is the one to do. You don't have to wait so long for these inductors to do their thing. Let's look at the induced EMF. Okay. So EMF induced, okay, stored in the inductor. So we have to go back to our circuit. So I'm going to just redraw our circuit. It's not that hard. I'm not going to keep scrolling up and down. It's easier to just draw it, really. Okay, so here's our inductor, here's our resistor, and we know our current is flowing this direction with a certain I of t, which we figured out what that was. We want the induced EMF, okay, in the inductor. This is the same thing that we called EL before, okay? So when we found that EL before, we found that to be minus L times our derivative with respect to t of the current. All right, so we found that. What was the equation that we found earlier? Let's do that. let's do our equation that we found earlier. So we had our E battery. So this is going back to the loop rule. All I'm doing is the loop rule here. I've got my R times I. I'm keeping it simple. I'm going to subtract off my L d dt of I of t, and that equals 0. This was my E of L. So if I do the absolute value, that's the absolute value of E of L. All right. So let's do it. Let's do the derivative. So we want the derivative with respect to t of I of t. So that's really the derivative with respect to t of this function e over r times 1 minus e to the minus t over tau. And what's going to happen? We're going to hit this term, okay, this first term. What's going to happen in that first term? We're going to get nothing, right? So we're going to say that ends up being nothing. Our second term, however, is d dt of our second term is going to be epsilon over r. I'm sorry, yeah. Our EMF divided by r negative times e to the minus t over tau. This one, not going to be 0. So that's going to be a thing. So we've got our di dt, and we're going to end up with something. What do we pull out here? We've got our tau. We've got 1 over tau. So we've got negative 1 over tau times our EMF over the resistance. And we're going to have another negative from the derivative. So I'm going to just put 2 negatives in there. This one might be this one from the derivative, this one from just this one. And so we've got those 2 things going on. And we have to multiply. No, not yet. We're not going to multiply by L yet because I want it equals. So where are we at? I need e to the minus t over tau. I think that's where we're left. Okay. So now let's go back to what E of L is. Okay. So we've got E of L is equal to L times these things, right? And let's do the absolute value so we don't have to worry about a whole bunch of garbage. 1 over tau is really 1 over tau is really our R over L. Okay, so let's do that. We've gotten rid of our negative signs, so that's fine. So we've got R over L, and then we've got our EMF. Now, that EMF is the battery EMF, okay, instead of our EMF induced, okay, so battery EMF, all right, and don't forget our e to the minus t over tau. Okay, well, Did I drop an R? I did. I dropped this R. I dropped this R. We don't want to drop that R. This R cancel. This L cancels. And we are left with whatever our battery EMF is. If we multiply that by e to the minus t over tau, then we're going to get that inductor's potential. Okay, the potential across the inductor that we subtract when we do our Kirchhoff's law. Okay. So good. Now, why do you want to just take the absolute value? Because you don't want to deal with all the minus signs. I think we actually have 3 minus signs in there altogether. And you just take the absolute value, okay? Figure out this magnitude, and then figure out your direction. The direction of the current, okay? And use, you got to use the Lenz's law, using Lenz's law. So if your current is going in that direction, it's going to fight it, and it's going to go in the opposite direction. If the current is increasing, okay, if I of t is increasing, and in our case, what we just saw was the I of t is increasing, so the EMF is going to fight that, and it's going to go in the opposite direction. Therefore, we subtract, right? That's the reason for the subtraction up above when we were doing our Kirchhoff's laws. Okay, we've run out of time, but I'm going to just take one final second to graph out. I want to graph this out, this one right here. Okay, so we're just going to look at the graph of our EL as a function of time. And here's time. And we're going to notice that at the very beginning, we start off with our max, right? So we've got our EL max at the very beginning, and then it's going to gradually go to 0. Okay, and what is it? 0.32 or something like that, or 3.7. 3.7, I think. That is our first tau. Okay, and should be the same tau. Okay, whatever tau we figure out, because it's the same old tau. So tau is still equal to L over R. Okay, that's our inductive time constant. I think that does it. And if we plug those other numbers back in, it doesn't take long. So this is a very quicks. I don't think so. Very quickly goes to 0. All right, guys, that's it. Thank you, and see you soon.